Hello, students. Dr. DA again. This is going to be a special lecture that you will have to watch on your own. We are going to talk about the energy transactions that happen when chemical bonds form. In our previous lecture, we talked about the Lewis model and how drawing these sketches called electron dot structures, we can represent the connections between atoms in molecules. Now, remember what we said before in that everything that happens in nature has an energy cost somewhere. And what I'd like to talk about during this brief lecture is what about the thermodynamics of chemical bonding? All right, that's what we're going to be talking about. So please get ready with the rest of your PowerPoint notes and let's embark on this little journey here. All right. First of all, remember that as we proposed in our lectures on thermochemistry, a chemical reaction essentially involves the breaking and the forming of bonds. When you break chemical bonds in a reactant, you are requiring energy. It's endothermic. When you form new bonds, since you're presumably going from a higher to a lower energy state, a more stable state, you are releasing energy. It's exothermic. So there is a way that we can use to estimate the enthalpy change of a reaction or the heat of reaction. If we compare the cost of breaking the old bonds, that is the reactants bonds, to the income from making new bonds. Again, kind of like a business transaction. We're going to talk about the bond energy, and let's define it as the amount of energy that it takes to break 1 mole of bonds in a compound, right? And the conditions are the following. Number one, that the bonds have to be for substances in the gas state, and that the breaking of bonds is what we call homolytic. In other words, for each pair of bonding electrons, each atom gets 1/2, or in other words, one of the 2 electrons. This is a table that represents just a sample of data of average bond energies for different kind of bonds. And you can take a quick look through it and see some trends that I'm going to discuss next. All right. So here are the trends. Number one, the more electrons shared by 2 atoms, the stronger the bond. So in this case, we're comparing bonds between like atoms, for example, carbon-carbon, or let's say carbon-nitrogen. Notice that a triple carbon-carbon bond costs more energy to break than a double bond, which costs more than a single bond. Similarly for the C-N bonds, right? The other thing is that when you calculate the bond energies of polyatomic molecules, uh, we have to be careful because it'd be interesting to know where the information comes from. For example, what does it cost to break the bonds in a molecule of water? Well, as it turns out, the first hydrogen-oxygen bond has an energy of 502 kilojoules to break, but the second one is actually 427. In other words, once you've broken one of the bonds, the other one is not necessarily going to have the same bond energy. And so what we do typically in these cases is we average over different bond energies, and we will put on the table the average energy of an OH bond, assuming that even though they're actually different, for this calculation, the average is enough. Now let's see how we approach the problem. Let's say that we're going to essentially take out the circumstances. The surrounding atoms, other factors are actually going to affect the actual bond energy, but we're going to make an approximation here. We're going to use average bond energies to estimate the heat of a reaction. And like I said, because bond energies are given for gases, this is going to work best when the reactants and products are in the gas state. Now remember, if you break bonds, you have to input energy. Therefore, the delta H for breaking bonds is going to have a positive sign. It's an endothermic process. Bond making is exothermic. The formation of a bond, the making of a bond should have a negative sign on it. So just like in any other process, if we basically add up the energy costs throughout the process, that is, the summation of all of the bond energies of broken bonds plus the summation of all the bond energies of formed bonds. Since the formation of bonds is negative and the breaking of bonds is positive, this ends up being essentially a summation of the bond energies of the reactants minus the summation of the bond energies of the products. Notice that it is not exactly the same as Hess's law when we considered heats of formation, right? So in that case, it was the heats of formation of the products minus the heats of formation of the reactants. But in this case, because of the change in the signs of delta H, it comes up this way. So be careful not to get those two processes mixed up, okay? All right, so here's the way we do. Just like we did before in thermochemistry, we are going to invent a path. We're going to say that we're going to take all the reactant molecules, we're going to break all of the bonds in those molecules and convert them back into pure atoms. So that is an invented path. That is going to require bonding energy input. In other words, this is going to be the bond enthalpy for all the bonds in the reactant molecules. And then we're going to take the atoms and from scratch form the chemical bonds in the products. So that would be the negative of the bond enthalpies because we're going in the opposite direction of the actual breaking of bonds. All right. So notice that in the one on the left, the cost of breaking the bonds is greater than the income, or so to speak, or the return of forming the new bonds. So the reaction on the left is going to end up being endothermic. In the reaction on the right-hand side, you can see that the cost of breaking up the bonds in the reactants is smaller than the return that you get from making the products. So that reaction is going to be exothermic. All right, don't forget, the delta H is the total energy input minus the total energy released. As we said, the bond enthalpies of the reactants minus the bond enthalpies of the products. Let's do a quick exercise here as an example. Let's say we're going to calculate what is the enthalpy change for this reaction. Hydrogen reacting with fluorine to produce hydrogen fluoride. Notice that because of the way we've built it, this is not exactly the formation reaction because we have kept that stoichiometric coefficient of 2 in front of the HF. If this were the reaction of formation, we would have to reallocate coefficients to make that HF product have a coefficient of 1. But we'll talk about that in a moment. Let's work through the reaction, okay? Remember that the formula is we're going to approximate the heat of this reaction by adding up the bond enthalpies of reactants and subtracting the bond enthalpies of the products. So let's make a little table. We're going to write out what are the types of bonds broken, how many of each, what is the bond energy per bond, and then what would be the total considering the number of bonds. Remember that in these types of exercises, we assume that all of the chemical bonds have to be broken, all right? So here is hydrogen bonds are broken, hydrogen, one of them at 436 kilojoules per mole. So that's a net of 436. For fluorine, we're breaking fluorine-fluorine bonds, just one of them at 159 with a total energy change of 159. Where did we get these numbers? From a table similar to the one that I just showed you a couple of slides ago. Now let's look at the products. Same thing again. We're going to write out what are the types of bonds formed, number of them, bond energy per mole, and then what will be the total for this particular case. So in this case, we are forming an HF bond, but we're making two of them because there's two molecules of HF. So each one of those has a bond energy of 565, which means that there's a total, that times 2, of 1130. So our total heat for this reaction would be 436 plus 159, that's the reactants, minus 2 times the bond enthalpy of the products, or minus 1130. And therefore, that gives you a net of minus 535 kilojoules. Now, if we wanted to calculate the actual enthalpy change, in other words, this is when we calculate the energy per mole. what would be the energy change per mole of hydrogen fluoride? Well, since this is for 2 moles, we divide by 2, and we get minus 268 kilojoules per mole. Remember, because this is the energy cost, or the energy release in this case, the energy change for the formation of 1 mole of HF, this is technically sort of like the enthalpy of formation, the standard heat of formation. Now, it's interesting to look at the actual value from the literature, which is negative 273 kilojoules per mole. So as you can see, for these kinds of reactions where everything is in the gas state, this type of approach gives you a pretty decent estimate. It's pretty close. I mean, in the world of thermochemistry, 5 kilojoules per mole at this level, at this amount, not a huge difference at this point, okay? So there you go, and you have some exercises in your homework from TRO textbook that will walk you through this. Just remember that when you do these exercises, you have to essentially break all the bonds in the reactants and form all the bonds in the products from scratch, okay? That's how it works. Now let's consider ionic bonds. One of the things that I think we brought up back when we studied the trends in ionization energies and electron affinities, this is in the previous chapter, is that the ionization energy of a metal is endothermic. So the guy who's going to be making the positively charged ion, it costs quite a bit of energy to make that, to take that electron away. On the other hand, the electron affinity of the nonmetal is typically exothermic because we are producing a more stable state. We're forming a favorable interaction. And so typically that represents a drop in energy. As a consequence, you have a negative delta H. But if you look at this, for example, between sodium and chlorine, on an absolute scale value, the ionization energy is larger than the electron affinity. So technically, if you add those two to form the compound sodium chloride, it should be endothermic. In other words, the ionization energy of the metal kind of overwhelms the energy cost here and makes it positive. However, if we actually look at the heat of formation of sodium chloride and actually of the majority of ionic compounds, number one, the energy of formation, the enthalpy of formation is negative. In other words, the process typically is exothermic. Not only that, but it's actually usually very large. You guys remember in your lab that you did for the formation of the oxides of group 2 metals, you should have gotten some fairly large values of the heat of formation, right? And they were all exothermic, right? So why is that? Why is it that the formation of an ionic compound is largely exothermic, whereas mathematically it should be endothermic? Well, the reason is that the formation of an ionic compound does not involve exclusively the formation of the corresponding ions. There is an extra step, and that extra step is the actual formation of the crystal lattice. Remember that in ionic compounds, every cation is surrounded by anions and vice versa. We call this a crystal lattice that maximizes the attraction forces between oppositely charged ions and minimizes the repulsive forces between equally charged ions. So this crystal lattice that is held together by this electrostatic attraction, right, of the cations and surrounding ions maximizes the attractions between cations and anions, and it leads therefore to the most stable arrangement. We're going to define something called the lattice energy, all right? This is the energy required to completely separate 1 mole of solid ionic compound into gas ions. In physics, you learn something called Coulomb's law, which essentially is used to calculate the energy between 2 opposite charges. And it goes something like this, okay? K is a constant. It's actually called Coulomb's constant. All right. Doesn't matter here. We're not going to use this quantitatively. But Q sub plus is the charge of the cation. Q minus is the charge of the anion. And again, we're not going to use units of charge actually in coulombs. We're just going to use, +1, +2, -1, -2 kind of thing. R here is essentially the distance between the ions, which can be calculated when we do what is called X-ray crystallography of ionic compounds. And we'll discuss that in a future chapter. What's important about this is the ratio. This tells me that this energy is going to be directly related to the product of the charges. In other words, the more charges, the bigger the number. And it's going to be inversely related to the distance between the ions. In other words, as the distance between the ions decreases, that energy increases. In other words, the more stable the ionic crystal lattice is. Let's look at some examples. Compare magnesium fluoride with magnesium oxide. If we calculate the lattice energy, we find that the energy for magnesium oxide is much larger. In other words, it takes more energy to break up that lattice, which means that it's more stable. What is the difference between these two compounds? It's the charges. Notice that in magnesium fluoride, you have a +2 charge from the magnesium and a -1 from the fluorine. And again, we don't add them up. It's just -1 because we're defining the interaction between one ion and another one. In magnesium oxide, you have a +2 for the magnesium and a -2 for the oxide. So the top part of that Coulomb's law expression is bigger for magnesium oxide, leading to a larger lattice energy. Let's compare two other compounds, lithium fluoride and lithium chloride. Again, the charges here are the same, +1 and -1. However, the lattice energy for lithium fluoride is much larger. So what we had to consider, therefore, is that second aspect of Coulomb's law, the distance between them. Remember that in the periodic table, we said that as you go down a group, you have bigger and bigger atoms. So that means that the fluoride ion, because it is smaller, it is going to be packed more closely with the lithium ion than the chloride ion is in lithium chloride. Since the chloride ion has a bigger atom, it is technically the charge density is a little lower. They're kind of like a little farther apart. And so because of that, you have a larger lattice energy for the lithium fluoride. Now you might ask, well, where did we get these numbers? Where did these come from? So we're going to discuss an approach here to calculating the lattice energy of a ionic compound. And it's something called the Born-Haber cycle, all right? Because these are things that typically we get them already formed, salts are already formed. It's hard to measure directly this lattice energy. So what we can do is we can calculate it by knowing the energies of other processes. So the Born-Haber cycle is a hypothetical series of reactions where we represent the formation of an ionic compound from its constituent elements. What we do is we're going to choose a set of reactions for which we know the change in enthalpy, and we leave one unknown, which is the lattice energy. Yes, essentially the Born-Haber cycle is an application of Hess's law. That's exactly what it is. We are going to invent a path using reactions for which we know the enthalpy change, and then we're going to solve for the missing or unknown one. Here's a representation of the Born-Haber cycle for the formation of lithium fluoride. Notice that we would start with the formation reaction, which we know already from tables. That is what it costs to make a mole of lithium fluoride from its constituent elements, and it has an enthalpy of minus 594.1. So what we're going to do is we're going to invent a path. First, we're going to pretend that we're going to make all these things into single atom gases. Then we're going to ionize them. We're going to make the lithium into lithium plus and the the fluorine into fluoride. And now we're gonna do the last step, which is the formation of the crystal lattice. And that's the one that we don't know. So what will happen is we're gonna have an overall delta H, which is essentially the heat of formation of lithium fluoride. And that should be the sum of all the energies of all the intervening steps. And our missing component is going to be that guy there, delta H5. All right. So let's go to our, let me come back here to our makeshift whiteboard, and let's build the Born-Haber cycle for this compound here. All right. So what we're going to do is we're going to take it step by step here. First, and again, the order in which we do it really is not that big a deal, but the first step we're going to do is we're going to take the lithium, which right now is in its solid form, and we're going to vaporize it. Now, actually, because this is a solid to gas transition, we don't call it vaporization, right? We actually call it sublimation. So this would be the delta H1, and we know that its value is 155.2. We're going to put all these in kilojoules per mole. And this is essentially sublimation. All right. Our second step is going to be taking now that lithium gas, right, and ionizing it into a lithium plus. We're going to release an electron from here, and this is going to be delta H2. And as expected, it is endothermic because we're trying to take an electron away. 520 kilojoules per mole. And again, we said this is actually the ionization energy. And we know that from tables. And I think in the unit where we discussed the periodic trends and the application of the quantum model to the periodic table, I left you in there one or two links to videos that show you, ways in which we can calculate the ionization energies. Okay, so now let's form our fluoride ions. First of all, what I'm going to do is we are going to take 1/2 of these fluorine molecules, and we're going to turn them into just a monoatomic fluorine gas atom. We're going to call this delta H3, and the cost of that is going to be 75.3 kilojoules per mole. And there's different ways you can call them. Tell you what, we can call this, sometimes they call it dissociation. But technically what it is you're breaking up, right, a fluorine-fluorine bond, right? So you could call this the bond enthalpy. And don't worry, I will have this sheet completed, uploaded, and posted to your Canvas page in case you're having a hard time seeing what I'm writing in here. Sorry about that. Okay, here we go. Step number 4 is going to be, we're going to take those fluorine gas atoms and we're going to add electrons to them. All right. So we got this fluorine gas. We're going to add an electron and we're going to form the fluoride ion. And delta H4 has an energy of negative 328 kilojoules per mole. And remember that in the discussion about periodic trends, we said that some authors will call this the electron affinity. In other words, the energy that is released as the anion is formed. Some authors will say, well, no, the electron affinity is the negative of that. In other words, the energy required to essentially take the electron away. But it's kind of like, let's just call it electron affinity for now, just to make it simple. Okay, our last step is where we take the lithium cations and we combine them with the fluoride ions to make the lithium fluoride crystal lattice. Delta H5 is our big unknown. That's the one that we don't know. We're trying to find out. So what we're going to do now is we're going to add up all of these processes, just like we did with Hess's law. And anything that's present on one side and on the other side of the equation essentially will cancel out as we add all of these. So for example, this lithium gas will essentially cancel out there, right? This lithium gas ion will cancel out over here. This electron will cancel with this one. This monatomic fluorine gas atom will cancel with that one. And the fluoride ion will cancel out with this fluoride ion. And I believe that if we go through that sequence, we're left with the lithium solid, the half a mole of fluorine on the left side, and on the right side, we're left with just the lithium fluoride compound. So that would be our overall. So our reaction would be lithium solid plus half a mole of fluorine gas. Don't forget that fluorine is one of those elements that exists. When we say fluorine without any other qualifiers, we imply that it's F2. And we're forming lithium fluoride solid. And we know that this delta H is the delta H of formation of lithium fluoride, which is minus 594.1 kilojoules per mole. So remember, this is essentially Hess's law, but specifically in this case, we call it the Born-Haber cycle. All right. So now basically we're saying that the sum of all the delta H's of the steps would be 155.2 plus 520 plus 75.3 minus 328 plus delta H5, which we don't know what it is, and that should total minus 594.1. So solving for delta H5, just simple mathematics, we get minus 1017 kilojoules per mole. Now, again, we find one of these interesting kind of like, what do you call it, naming kind of paradoxes, and that is that some authors will say that this is the lattice energy. They like to keep that negative sign in here just to remind us that it is a very exothermic process, and it is what essentially drives the process of formation of an ionic compound. In other words, it kind of highlights the fact that the formation of the crystal lattice is responsible for the favorable energy change that occurs in forming a ionic compound, where the actual formation of the ions in and of itself is not sufficient. Other authors prefer to think of it as, okay, the bigger the lattice energy, the more stable the compound. And so some authors will say that the lattice energy is actually the opposite, the negative of this. In other words, 117 kilojoules per mole. That's the definition that we proposed, which was how much energy does it take to break up a mole of formula units of this crystal lattice. So here's what I recommend. When you are reading your textbook, make sure that you know which of the two definitions your author favors. Does he favor or does she favor the definition where you focus on the actual energy change, or do they focus more on the stability of the crystal lattice in terms of, well, how much energy would it take to break it into pieces? All right, cool. All right, so let's come back here to our PowerPoint and let's finish this out. As we said, basically we have minus 117 kilojoules. That's what this step actually costs. Actually, what it actually, the energy change for this step. Like I said, you can call this minus 1017 kilojoules the lattice energy, or you can say the lattice energy is the reverse sign of that one, the plus 1017, right? We're going to talk a little bit about metallic bonding. We said at the beginning of our discussion that there are three large categories of bonding: ionic, covalent, and metallic. Ionic, as we saw, the process is driven by the stability of the crystal lattice. Covalent bonding is driven by essentially the balance between how much does it cost to break bonds in the reactants versus how much is released by forming bonds in the products. Now with metals, it's a little different. Remember that metals have very low ionization energies. They can easily lose electrons, and that's why they make cations. But remember that in a solid metal, what you have is just the atoms of the metal. So there's nothing to really give the electrons to. So the theory is that the valence electrons of the atoms in a metal are shared as a pool. It's kind of like as if the metal atoms are organized as a set of nuclei with core electrons, which technically is kind of like a sort of like a sea, or let's say a group of islands of cations in a sea of electrons. In other words, the model proposes that the electrons are delocalized. They're not attached. I mean, the valence electrons are not attached to each atom that they belong to. It's almost like they are kind of spread out throughout the metal structure. And so because of this, what you have is you have these cation, quote unquote, islands that are strongly held and attracted by this sea of delocalized electrons. Here's a picture, let's say sodium metal, which is not found in nature. We make it by process to purify sodium metal. If you could look at the atomic structure, you can see where what you have is like these islands, the inner spheres here, the purple looking ones, those would be essentially the nuclei of the sodium atoms surrounded by the electron cloud of their core electrons, which for a single sodium atom would be 10, right? 10 electrons, just like neon. I'm sorry, yeah, just like neon. And then what you have is you have that valence electron of each atom is now essentially delocalized all over the structure in the form of an electron sea. So that's the model for metallic bonding. It makes an interesting prediction. It says that because the electrons are delocalized, they should be able to move throughout the metallic crystal. Now, electrical conductivity occurs when charged particles like electrons are able to move throughout a structure. So this model predicts that if I apply a voltage, in other words, a potential difference across the metal, I should be able to get those electrons to move, in other words, to form a current. Bottom line, the model predicts that metals should be good conductors of electricity. And that is the case. Metallic solids do conduct electricity well. We'll discuss a little more about metallic bonding again in our study of solids later on. But for the moment, that's all that you need to know. All right. Okay. We are pretty much done with this topic. And I hope you get a chance to look at this lecture before our next actual live Zoom meeting, because we are going to go ahead and move on to the next unit. We're going to apply the Lewis model and start making predictions about the shapes of molecules, about the overall property of polarity of compounds, and then we're going to start proposing some theories regarding how does chemical bonding actually happen. So until then, have a good time, stay safe, peace out.